Lecture 12b is the linear algebra portion of Lecture 12 for differential equations in linear algebra. We're going to do geometric composite transformations in 2 dimensions and matrix multiplication. And I will talk about how matrix multiplication is related to dot products. I hinted at that before. Also talking about inverse linear transformations and inverse matrices. And before we get to that, we'll need to talk about inverse functions in general. So some pretty interesting topics here. Let's jump ahead to the linear algebra portion and think geometrically. We started talking about linear transformations geometrically, and that really is important for the big goals of this course, including the main relationship between linear algebra and differential equations. This change of coordinate systems was something I really emphasized the first couple lectures. That's related to geometry. And we can ask, for example, questions like this. What happens when a rotation and a reflection are composed, where I do one after the other? Well, not just any rotation and reflection are going to be considered here, but particular examples. Let's consider first the clockwise rotation by 90 degrees. So T is going to be a linear transformation from the plane to itself. The domain and codomain are both R2. And it's going to be defined by a certain equation. I'm going to tell you the formula, how to figure out the formula for this before I show it to you here. And what I'm about to say as far as figuring out the formula is real important. I don't write it in the actual PowerPoint itself, just writing it on the board. What you want to do to figure out what matrix will implement this linear transformation is you want to figure out how the linear transformation affects what are called the standard unit vectors or the standard basis vectors. And in the plane, if you think of the vectors as arrows, instead of the points they're associated with, this vector right here that ends at 1 and has components 1, 0 is one standard basis vector. In physics, that's often called I hat, okay? And later on, we will more commonly call it I hat sometimes. And another one pointing straight upward, this is also 1. It would have components 0, 1, and in physics, that's typically called J hat. What you want to do is you want to figure out how does the particular geometric transformation affect those particular vectors. And if you can figure out how it affects those standard unit basis vectors, it tells you right away what the matrix should be. Okay? So we want to rotate this around the origin by 90 degrees. So, thinking in terms of mappings, I hat, 1, 0, will get mapped to J hat, 0, 1. And J hat will get mapped to a vector like this that would have components negative 1, 0. And because of that, it turns out that the trick is what I hat gets mapped to, 0, 1, becomes the first column of the matrix, and what J hat gets mapped to, negative 1, 0, becomes the second column of the matrix. That is the formula for this linear transformation. Here's what I mean. Actually, I'm calling the matrix B here for a reason, because it's related to the last lecture, 11b, about linear algebra. T of x is going to be B times x. This is going to be my matrix B. Notice the first column right there, 0, 1, is what 1, 0 got mapped to under the 90-degree counterclockwise rotation, 0, 1. And the second column, negative 1, 0, is what J hat, 0, 1, gets mapped to under 90 degrees counterclockwise rotation around the origin. And this will turn out to be the correct formula in general for an arbitrary vector. No matter where you put the vector, it could be down here with components x1, x2, say. You want to rotate that around the origin by 90 degrees, it'll get mapped to a vector. You can see this simplified formula that'll have components negative x2, x1. And if you try some examples, you'll see that that makes sense. Okay? This is a right angle right here. This is a 90 degrees rotation. I'm emphasizing right here, as I've been emphasizing recently, that a matrix times a vector, by definition, our definition is a linear combination of the columns of the matrix with the entries, the coefficients of the vectors, the components, as the weights. So I have x1, the first component of the vector, times the first column, 0, 1. Then I have x2 times the second column of the matrix, negative 1, 0. Those are scalar multiplications, then I add the results. Actually do the scalar multiplication and additions, you get this when you simplify it. Okay? So this turns out to be the thing you want to do. This is related to dot products. Maybe you know this already. Notice that if you took the first row of the matrix, and you could call it a row vector if you wanted to, it would be a two-dimensional row vector, and converted it to what we've been talking about with vectors, a column vector. Note, right? That row as a column, because we've been typically dealing with vectors as columns, not that you have to, but that's what we've been doing. Dot that with, let's say, an arbitrary vector x1, x2. What do we get? We get, multiply the first components, 0 times x1, add the product of the second components, -1 times x2. That simplifies to negative x2, which is the first component of the answer. Effectively, we're dotting the first row of the matrix with this column vector to get the first entry of the answer, the first component of the answer. What about the second component? Dot the second row with this vector. If you want to think of it as a column vector, you could. 1, 0, dotted with x1, x2. Gives you 1 times x1 plus 0 times x2. Simplifies to x1, which matches the second component of the answer. Okay? So you don't have to think of it in terms of the linear combinations. You can just jump from here to here if you think about these dot products in your head. Though, if you don't have to draw the dot product and you don't have to make these rows become columns, you can just pretend you're doing a dot product with a row vector and a column vector. Okay? That'll be a more helpful way to do products of a matrix times a vector, and as we will see today in this lecture, 12b, when you multiply two matrices as well. Let's also do a reflection of, say, 45 degrees through the origin. A reflection across the 45-degree line through the origin. I'm calling that S. Let's once again think about what happens to the standard unit vectors, also called the standard basis vectors. 1, 0 and 0, 1, I hat and j hat. I'm reflecting across the 45-degree line, assuming the scales on the axes are the same. I hat's going to get mapped to j hat, and j hat's going to get mapped to I hat. So j hat's going to be the first column of the matrix for this, and I hat's going to be the second column. 0, 1 is the first column, 1, 0 is the second column. 0, 1, j hat is what I hat got mapped to when you do this reflection. I hat, 1, 0, is what j hat got mapped to. Here's the definition of a matrix times a vector is a linear combination of the columns of the matrix. Simplifies to this. You could also think in terms of dot products. The first entry of the answer should be 0, 1 dotted with x1, x2. 0 times this plus 1 times this is going to give you x2. The second component of the answer is going to be 1, 0 dotted with x1, x2. 1 times x1 plus 0 times x2 is x1. You can think of it in terms of dot products. What are the composite transformations? S compose T and T compose S. Here you can do both of them because the dimension of the domain and codomain are the same. I did mention in lecture 11b that if you can do S compose T in general, you can't do T compose S because the dimensions might not match up right. But if the dimension of the domain and codomain for both S and T are the same, you can do both compositions. However, composition of functions is in general not commutative. You're not going to necessarily get the same answer, and in fact, we do not here. To actually find the formulas for these compositions, you can use matrix multiplication. A times B and B times A. Make sure you do it in the right order. S compose T of X. Now, first realize when you actually think about the composition, that means that you go from right to left. You're applying T first and then S. If you're writing in terms of function notation, you would write, this is S of T of X. The inside function is t, the outside function is s, so you do t first, then s. In terms of matrix multiplication, you multiply by b first on the left of x, then multiply by a on the left of b times x. I didn't put parentheses in here because this kind of thing is associative. You could think of it that way, b times x first and then times a on the left. You also could think of doing a times b first and then put that on the left of x. And that's really the more efficient way to do it typically. So here's a and here's b. Double check that. Here's a, here's b. 2 by 2 matrix times another 2 by 2 matrix can be done because the inner twos match, and the answer is going to be a 2 by 2 matrix. To find the entries quickly, you can think in terms of dot products. Listen carefully. The entry, the 1, 1 entry in the first row and first column is the dot product of the first row of the matrix on the left with the first column of the matrix on the right. 0 times 0 plus 1 times 1 is 1. The 1, 2 entry, first row, second column of the answer is the dot product of the first row on the left with the second column on the right. Got to practice this to get good at it and not make a mistake. 0 times negative 1 plus 1 times 0 is 0 plus 0 is 0. The lower left entry, the 2, 1 entry, second row, first column, is found by doing the dot product of the second row on the left with the first column on the right. 1 times 0 plus 0 times 1 is 0. In the lower right entry, the 2, 2 entry, second row, second column, do a dot product of the second row matrix on the left with the second column in the matrix on the right. 1 times negative 1 is negative 1, plus 0 times 0 is negative 1. And then if you multiply this matrix times this vector, you get this. You can do it in the opposite order, you get a different answer. You should take the time to double check this. Hopefully I've not made a mistake. Yes, and these two functions, these two linear transformations have different final formulas. They also have different matrices here and here. Matrix multiplication and function composition is not commutative, right? That's a pretty significant thing. And when people were first dealing with matrices, they didn't realize that happened. They didn't really know maybe necessarily the right way to multiply matrices at first. People experimented with it. I think it was a big point of revelation to somebody, one of the founders of quantum mechanics, I don't know if it was Heisenberg or somebody else, to realize that matrix multiplication is not commutative and that was actually what you want to happen, that it not be commutative. All right, let's do another example. Let's compose a rotation in one direction with the corresponding rotation in the opposite direction. Think for a second, what should happen? I rotate by 90 degrees counterclockwise and then rotate by 90 degrees clockwise. I should get back to where I started. No matter where I start, actually. Here's our counterclockwise rotation by 90 degrees. This is the same function as the previous slide. What about a clockwise rotation by 90 degrees? I hat, I'm not going to draw, I hat, if I go clockwise by 90 degrees, is going to get mapped to negative j hat, going straight down. And j hat's going to get mapped to I hat. 1, 0 gets mapped to 0, negative 1. The first column is going to be 0, negative 1. And j hat, 0, 1, gets mapped to 1, 0. The second column is 1, 0. Simplified, it simplifies to that. What happens when I compose these functions, say by multiplying their matrices? In both cases, we actually get the same answer this time. And I didn't do this, but I could have. The final answer is the same in both cases and equals the original input vector. I should have done that. The output is the same as the input. These x's match. Right here. These things match. This matrix that you see in both cases, here and here, is a very special matrix that you get after multiplication, and it's the same in both cases. It's called the 2 by 2 identity matrix. If I multiply the identity matrix times any vector, I get that vector back. It's kind of like multiplying by 1. It's analogous to that. Okay? This is going to come back. We're going to think about this more, but let's go on. Inverses of bijective functions. What does bijective mean? Bijections are one-to-one and onto. A bijection is a noun. Bijective is an adjective. If a linear transformation T from Rn to itself is both one-to-one, injective, which also means its kernel must just be the zero vector, as we've talked about. That's special for linear transformations. If it were a nonlinear transformation, something that would get mapped to zero might not necessarily be the zero vector. And onto, which is called surjective, which also means the images all of Rn. And as we've talked about, in order for such a linear transformation to be both one-to-one and onto, the domain and codomain would have to be the same dimension. Then we sometimes call T a one-to-one correspondence, but we also say it is bijective. T is bijective, or T is a bijection. I'll probably use both words, one-to-one correspondence and bijection, or I will say it's bijective. Any one-to-one correspondence between a domain and a codomain must necessarily have an inverse function. This is something you should have learned in algebra before college. I mean, high school algebra. Maybe you've forgotten it. If this is your domain, call it A, and this is your codomain, call it B. And you've got a function that's mapping from A to B, and that function is both one-to-one and onto, then given any little b over in the set capital B, there must be at least one thing in A that gets mapped to it, because the function's onto, and there actually can only be one thing in capital A, it's unique, that gets mapped to B. B is f of A, because f is one-to-one. We essentially define the inverse function to go the other direction, f inverse, to say f inverse of A equals B. Swap around the roles of A and B. And that holds true even if we've got nonlinear functions. When that's the case, we say the function is invertible, and standard kind of notation for an inverse function is to put a -1 sign, -1 up there as if it were a power, but it is not a power. This is unfortunate notation, but it is standard. T to the -1 is not a power. In fact, I shouldn't even say T to the -1. I should say T inverse. It's not the same as 1 divided by T as a function division. Not the same. Invertible functions and their inverses undo each other. In general, if f goes from A to B, its inverse will go from B to A, like I have on the board there. Sorry if that's off the screen there. You can't quite see this over here. I had a B there. Then they undo each other when you compose them. In either order, you get an example of an identity function. In this general setting, f going from A to B and f inverse going from B to A. So the domain of f is A, the codomain is B. For f inverse, the domain is B, the codomain is A. And when you compose them in this direction, in other words, go from right to left, do f inverse first, then f, and an arbitrary little b and capital B. That means this. You're going to get little b itself. If you do it in the opposite order for a little a, an arbitrary little a and capital A, you're going to get A itself. You could define a function called the identity function in both cases. This is the identity function from B to itself. This is the identity function from A to itself. These are definitions of functions that map points to themselves. You could say that's another way to think about this. And in fact, without bothering to write inputs, you could also write then that f circle f inverse equals ID sub B, and f inverse circle f equals ID sub A. So there I'm purely thinking of the functions as abstract objects and not thinking about their inputs when I write those things. just focused on the function names there. But here's what they do to inputs. This applies in general for functions and their inverses, functions when they are invertible. It holds true for linear transformations as well, because linear transformations are functions, as you should never forget. But is the inverse of an invertible linear transformation also a linear transformation? You would hope so. If t is bijective with an inverse function, t inverse, oh, I made a typo here, I forgot to say, and linear, it's a linear transformation. Another mistake I need to fix before I put it in the Google Drive. Is the inverse function, which will exist by what I've just talked about, necessarily linear? In other words, is it OP, operation preserving? I'm going to show you the argument for this, that it is operation preserving. It's a tricky argument, and it would be difficult to figure out this argument on your own from scratch for most people. It involves doing some tricky kinds of things. It is linear, and here are the details. The first trick, and this is probably the hardest trick, here I've got an arbitrary linear combination of two vectors, alpha u plus beta v, is to realize I can replace u with t of t inverse of u and replace v with t of t inverse of v. And what's trickier is realizing that that's a good idea to do that in the first place. I mean, certainly you can because of the previous slide. T and t inverse are assumed to be inverse functions of each other, so therefore u would be t of t inverse of u, and v would be t of t inverse of v. But knowing that that's a good idea in the argument is the hard part. Another hard thing is the next step, to realize I should use the linearity of t. I'm assuming t is linear. I've got a linear combination of t values, t of t inverse of u and t of t inverse of v. By operation preserving property, that's t of the corresponding linear combination of these things with the alpha and betas in front that I have in front here and here. Kind of using the operation preserving property in the opposite direction, but it is true. So this is definition of inverse functions to get from here to here. This is operation preserving nature of t because I'm assuming it's linear. It is therefore operation preserving. Okay, so what? On the other hand, I can also say by the definition of inverse functions that alpha u plus beta v equals this. There I'm just using the fact that t and t inverse are assumed to be inverse functions. This quantity equals t of t inverse of itself. Okay, what next? Use the fact that t is also 1 to 1. It is bijective, so it's 1 to 1 and on to. T of this equals that, but t of this also equals the same thing. These two things here and here are equal to each other because they both equal alpha u plus beta v. Since t is 1 to 1, that means the inputs must be the same. This whole thing here must be the same as this whole thing there. And that means we're done. The inputs here and here must be equal, which is exactly what I'm saying here. And that means t inverse is operation preserving. T inverse of this linear combination is the corresponding linear combination of t inverse of u and v themselves. So t inverse is linear. So it's got a matrix. If the matrix of t is called A, probably we should call the matrix of t inverse A inverse. And just as t inverse notation does not mean t to the negative 1 power, so A inverse notation technically does not mean A to the negative 1 power. However, you could kind of take it to mean that, but I don't want to get into it here. As it stands, it's just the inverse of A. What is A inverse, though? How is it found? Row reduction of a certain augmented matrix to reduce row echelon form. But this augmented matrix doesn't contain just one right-hand side numbers. It contains columns of numbers. It contains 3 of them for a 3-dimensional example, n of them for an n-dimensional example. We're going to do a 3-dimensional example here in a minute. In the abstract, the row operations are to take an augmented matrix of this form. A is n by n. I here is taken to be the n by n identity matrix. I need to tell you what that is here in a minute. Both of these matrices are n by n, so the combined matrix is n by 2n. Still n columns, but now double the number of rows. Still n rows, but double the number of columns. And we do row operations to reduce row echelon form until we get I, the identity matrix, on the left. And if we've done that, then A inverse will be on the right. And this is once again n by 2n. If it's not possible to get I in the left part of the answer, then A will not be invertible, and that would mean T was not invertible either. I'm not telling you why this works. On my blog, infinityisreallybig.com, my textbook Visual Linear Algebra Online, section 1.9, I think, or 1.8 or 1.9, one of those two, I explain why this is done. I'm not taking the time to explain it here. I is the n by n identity matrix. You could just call it I for short. Technically, to be a little bit more precise, you could call it I sub n. It's this matrix. Bunch of 1s and 0s where the only ones are on the main diagonal from upper left to lower right. That's called the main diagonal of a square matrix. Square matrix has the same number of rows as columns, n by n. You put 0s everywhere else. This is the main diagonal, upper left to lower right of a square matrix. There is a non-main diagonal from upper right to lower left, but we usually don't think about that. The more important one is this main diagonal, and that's why it's called the main diagonal. This has the property that you multiply times any n-dimensional vector, you get that vector back, which is the same as the identity function on Rn applied to x, for all x in Rn. The identity function on Rn maps any input to itself. The output is the same as the input. And you can check, I'll let you do it, take in times any n-dimensional vector. Imagine multiplying this by an n-dimensional vector, x1, x2, x3 through xn over here, column vector. You will get that vector back. You should check that. Here's our last slide. Then I am going to show you some Mathematica just like I did in the first lecture. Here's an example. I'm not going to take the time to double check all the calculations. Here's our linear transformation to R from R3 to itself. Here's our matrix. I could simplify this. Maybe I should quick. Thinking in terms of dot products of rows with this column vector. 4x1 plus 4x2 minus 3x3. Whoops. Is the first component of the output. Dot product of the first row with the column vector. Dot product of the second row with the column vector is the second component of the answer. 10x1 plus 7x2 minus 4x3. And then dot product of the third row with the column vector is the last component of the answer. 3x1 plus 2x2 minus x3, if I've not made a mistake. Looks good? Why do you pick this particular matrix? It turns out that this particular matrix has a nice inverse, not having to involve with fractions. So you should take the time to double check these row operations. Notice that this 3 by 6 matrix is of the form A and I, or I3 if you prefer. And these are the row operations to get it to reduce row echelon form, where we now have I3 over here, and this thing is A inverse. I'm skipping some steps. I'm doing more than one row operation sometimes. For example, to go from here to here, I did 3 different row operations. I first multiplied row 1 by 1/4 to get it to be this row. Then, thinking in terms of that row with the second and third rows, I multiplied this by -10 and added to the second row and put the answer in the second row to get a 0 there. And I also multiplied row 1 by -3, added to row 3 here to get a 0 there. To go from here to here, I swapped rows 2 and row 3, and then I multiplied the new row 2 by -1, etc. You should take the time to double check this. And this is the inverse function, or the inverse matrix, I should say, right here. That's A inverse. And you could write the formula for T inverse like this. I use the same symbol for the input here for the inverse function. I could have used a different symbol like Y instead of X. You should take the time to check that A times A inverse equals A inverse times A equals the 3 by 3 identity matrix. Okay? Take the time to check that. Let me show you some things on Mathematica. I haven't shown you the linear algebra stuff that you can do in Mathematica yet, but I think this would be a good time to start. Here I'm entering the matrices back from the rotation and reflection examples. If you want to see a matrix, well, realize that when you can get the matrix, first of all, from the writing assistant with this button right there, at least in the 2 by 2 case. But when you look at the matrix, it does not make it look like a matrix unless you put / matrix form at the end. If you want to multiply two matrices, A times B, you do not put a star. In Mathematica, you put a period. A decimal point if you prefer. That does the multiplication. And if you want to see it as an ordinary looking matrix, you do the / matrix form. I actually don't have to do the matrix form with the / at the end, but don't worry about that. There's another way to do it. Here's A times B, here's B times A. They are different with that example. If I change A, then these will get updated. And this is the example where A and B are now inverses of each other, and so you get the identity matrix when you multiply. The matrix inversion. Well, here I'm showing you I can actually do the matrix form in front with square brackets. This row reduce is row reducing that matrix that I just showed you a couple minutes ago. This is A over here, this is I. Row reduce does the row reduction matrix form, shows you the output and the answer, and this is the same as A inverse. Inverse A will also find A inverse. Notice that this matrix is the same as this matrix. And we can check that the product of these things gives you the 3 by 3 identity matrix. Notice again the product is done with a dot, not a star. Okay, that's essential to realize. Thanks for watching.